Let's look at SDC constraints. In this module, we'll identify what design objects are, and the constraints on the different types of design objects. Then, we'll look at design-level constraints, environmental constraints, and all the different types of constraints that are in an SDC format. Constraints provide all the specifications that our design must meet through optimization. So you can have constraints for clocks, external constraints, power constraints, yield constraints, net delay constraints, environmental constraints, and even constraints for design rules for manufacturing. Now, you can use a certain constraint to tell the tool what you need to achieve through these constraints and then, later on, verify the same design through these constraints. So for this course, we will only stick to the timing-related constraints and ignore all the other ones. The SDC constraints are the standard format for writing constraints in the design industry. STA tools have their own style of writing constraints. Each tool dumps out its own type of TCL syntax constraints. But at the same time, all of these writing variations or styles that you see are considered equivalent for the purposes of writing your constraints. When you write out your constraints, you might write it out in a simple format. But something that is generated from a tool might use different floating point numbers or specify get_ports to identify ports. All these different variations are functionally equivalent. It's just that some tools prefer one way or the other. If we were to group the SDC constraints, you would group them into operating conditions or constraints that were environmental related, your design rules or power related and timing related, and finally wireload models related constraints. So, all of these different constraints are specified to achieve the common goal, which is to meet timing for your design. In order to set the constraints, let's categorize the design into different design objects. You might have your design, which is the container for the entire circuit, you might have cells or blocks, or have ports, which is an entry or exit point into the design, and your pins, which are necessarily the ones that are around your blocks for an instance or a hierarchical port or design or a sub-design. Clocks are the sequential cell drivers. Nets are the wires or the interconnect between the cells and the design ports. Your operating conditions are the ones that affect the entire chip, or if you're constraining a block in this case, then those that affect the entire block. You would apply constraints like power constraints or wireload models to the cell or the block object. To tell the tools what the surrounding environment looks like, you might apply environmental constraints to a port object, including set_drive or constraints like that. To find and use a port object, you can use a get_ports command. Pins are like ports of your sub-design or inputs and outputs to a cell. So any constraints that need to be applied at the hierarchical port level of your design would be applied at the pin level. If a port is defined as a clock, then that becomes a clock object. So you would define period, waveform or anything related to a clock on a clock object. You can apply timing constraints to net objects. Wireload models are typically for the purposes of calculating the delays of these net objects, so you can get the net object and identify what the delay on that particular net is. The design rule constraints are applied at the design level. These design rule constraints must be met so that your design can be manufactured. These rules actually come from the fabrication process, and you must set these design rule constraints according to the fabrication process. Operating conditions are something that you would apply at the design level. We have specific library files created for a specific set of operating conditions. So, you can specify just the library and that in itself is sufficient. But if you are reading in multiple libraries and you want to use a specific set of operating conditions, then you should use the set_operating_conditions command to set that particular operating condition to use as your default for timing analysis. As the design process varies, you might have to change this operating condition often to get different timing data. A corner is one specific set of process, voltage and temperature. For multi-mode multi-corner designs, you'll have a particular design being verified for different modes and different corners. If you are verifying your timing across multiple corners, then you will have to specify your operating conditions according to the corner that you're currently verifying. Wireload modes determine how the net delay calculation happens. In the case of the top mode, all the net delays in the entire design use the top model. In the case where you have a wireload model that is considered as large, and if it encompasses the entire area of the design, then the STA tool uses large to calculate the net delays throughout the design. Obviously, this is very pessimistic. Use this only for conservative estimates. The opposite end is using a zero wire load model. If you just want to see if the design will meet timing even without any wire delays, then you could use the zero wire load model option. To force a particular sub-design to use a different wire load model than the one from the top, you can specify the set_wire_load_model command for that particular sub-design. Another wire load mode is the enclosed mode. Let's say if your entire design is 8,000 units, and the average block is 4,000 units. Block B would be encompassed under 4,000 units, whereas the entire design would take 8,000 units. Then for the enclosed mode, Block B would choose the 4,000 units because it can be enclosed in the 4,000 unit model. But for the rest of the design nets, the tool will use the larger one, which is the 8,000 unit wire load model. Now let's extend the same logic to another example. If there are blocks A and C, they will fall under the category of small WLM of, let's say, a 1000 units. Then you would have all the nets under block A and block B use the small WLM, which falls under the 1000 units. So, from that example scenario, if we look at multiple nets in this design, net 1 uses whatever encompasses that particular net 1, which is block B, and uses average WLM. For net 2, the entire design is encompassing it. Neither block B nor block C can contain that particular net 2. So net 2 must use large WLM and net 3, because it is enclosed in block C and must use the small WLM. In the segmented wire load mode, the tool breaks down the entire design net into small chunks. Depending on what encloses that particular chunk of the net, that model is what is used for that particular piece of the net. If you look at the bottom right, the segmented mode shows the different segments of the net and what wire load models are used. In the case of net 3, all of net 3 is encompassed in block C and uses small WLM. But if you break down net 2, block A net 2 will use small WLM, block B net 2 will use average WLM, and the design net 2 uses the large WLM. Block C net 2 uses the small WLM. So you're breaking down the nets into smaller pieces. This sounds like the most logical choice, but because the tool varies in how it does the optimization, the computation is intensive and it runs very slowly. Also, if there are nets that fall under critical paths, then the wire load model often changes because of the block that encompasses that particular net. Thus the models and the delays that the tool generates for these nets become unreliable. Wire load models can be used for timing verification. But, in general, they are not as reliable for optimization, and segmented is specifically not a recommended model for net delays. Wire load models are applied during synthesis to determine the wire delays. These wire load models are categorized based on area. So when there are no wire load models specified, the tool automatically selects the default from the library. If you want to specify the model for a block, you can specify the set_wire_load_model command. So, you usually have a wire load mode and wire load model, and both of these in combination, determine what wire load model to use for a particular net. When nothing is specified, it goes based on what the defaults are from the library. The environmental constraints are typically applied at the port level. The environment of the chip obviously has an influence on your chip performance, and you need to model the environment in terms of the constraints. A driving cell is something that drives the input of the chip, and the load is what must be driven by the output pins. Both of these must be accounted for when you're designing your chip. For example, how much load can an output drive? Or what is the driving cell that is driving your input pins? Both must be specified for your design to work properly. If you know what specific cell is driving the input of a pin, then you can set that using the set_driving_cell command. By defining the driving cell, you're defining what the strength of the incoming signal is, or its capacity to drive the input and the fan-out of that input pin. So, you can use the set_driving_cell command to tell the STA tool to use this SDC constraint to determine the driving cell of that input pin. You can define what the load of an output port is, which is the total amount of capacitance that the port has to drive using the set_load command. Or, you can also specify the set_fanout_load and set_port_fanout_number, a combination of these two to determine the load per fanout and how much fanout it has. Both of these in combination can determine your total load that this particular output pin sees. Look at the notes to see examples of port fanout number and fanout load values and examples. You can define the environment of a chip using the set input delay and set output delay commands. Using the set input delay command, set the arrival time on a port relative to a clock. The set input delay command specifies a delay value and whether it's rise or fall and what clock it's relative to. In this example, the input signal arrives at the IN2 with respect to the CLK2 clock, and it arrives 4.3 nanoseconds after the active edge of CLK2. For bidirectional ports, you can specify the path delays for both input and output modes. For multiple clock scenarios where a particular input has to go to multiple clocks, then you would provide that relationship using the add delay option. If you want to specify that the first example command shows the input delay in relation to clock 1, and the next one is the input delay in relation to clock 2. When you specify the add delay option for each of the clocks, then that will give the multi-clock scenario that you need when that same input is going to different clocks in the design. Set the output delay using the set output delay command for all the output ports in your design. This will ensure that all the registered output paths will meet the timing specified. The tool uses this value to constrain the output ports. The set input delay and set output delay are used at a block level, in place of the set driving cell and set load commands when you're unsure, or when you are budgeting the constraints based on the modules in the design. The create clock command creates a clock object with an ideal signal. It specifies the period, waveform and the ports or pins that are connected to the clock source. The duty cycle can be derived from the period and the waveform, which is the edges itself. In the first example shown above, the command defines a clock, which is an ideal clock. It is connected to a port called PHI1. The ideal clock is named clock 1 and has a period of 10 nanoseconds and a leading edge at 0 and a trailing edge at 5. So, the duty cycle is 50%. For the second example, the period is 20. The ideal clock is defined as clock 2. It is set on pins named clockGN 1, Z, clockGN 2, Z, clockGN 3, Z, and these three are pins. This clock has a period of 20 and a duty cycle of 50% because the waveform is defined as 0-10, so leading edge is at 0 and trailing edge is at 10. These three clocks, which could be generated clocks, could have also been defined using the create generated clock command, and then any modifications on the source clock are inherited by the generated clocks, that is discussed separately. Just like all other signals, clocks also have rise and fall times. The fanout of the clock is much greater than those of most other signals. _clock _ slew degrades as the clock has options for setup as well as hold. You can define separate uncertainties for maximum transition times on all signals, including the clock. In this example, we are setting different uncertainties for setup and hold. So if you want to model the real nature of these values, you need to add the transition uncertainty is added latency to the ideal clock. Whereas in the propagated mode, you would want to set uncertainty only to the jitter value rather than including both the rising as well as the ideal clock and a slew of 0.25 latency as well as the network latency using the set _clock _ latency object, and the clock object will indirectly call the related ports. These would include the rise and fall transition times as well. So any ports that are related to CLK1 for when there is no transition time uncertainty and any other values that you set on. As the source latency is concerned, like all other signals, specify the source option. Have rise and fall times. But when you don't specify the source option, you're modeling the network latency by other signals. In this example, the ideal clock versus the actual clock has different latencies. You can define different clock latencies for transition times using the early and late options. Where after early relates to hold and late relates to define it with specifics. When you define clock latency, so if you want to model the real nature of a clock, that you're setting the latency transition time, that it is the source latency and latency to the ideal clock. Generated clocks are helpful when you want to model a particular clock and inherit all the properties nanoseconds on the rising edge of the ideal clock, and a slew of 0.25 nanoseconds on the falling edge. Notice that get underscore generated is calling the clock when you have weird numbers or weird divisions that are happening like 1/3, which must use floating point numbers on the clock. The calculations are harder for certain that are related to CLK1 will all get the same slew and uncertainty. In the case of a generated you set on, you don't need to worry about such things because you are just implying that it's 1/3 of a master clock. The fan-out of the clock is much greater than those of most other signals. A generated clock is a fraction or a multiple of the source through these cells. As we discussed earlier, the purpose is to inherit the maximum transition times on all signals, because you can use it to model the outputs of multipliers and clock dividers. You need to refine it with generated underscore. So if you want to model the real nature of a clock, you need to add the transition times. It helps with defining the relationship between the ideal clock, especially when these clocks have data talking to each other or signals talking to each other. Nanoseconds on the rising edge of the ideal clocks to define their base period. You already have an established relationship, and all the floating point calculations become easier. Calling the clock object in the first command object, the generated period is related port, and the one at the bottom shows that it's twice the period. On the clock object. You can vary the duty cycles related to CLK1 will all get the same slew and uncertainty in any other values that you set easily and verify any data transfers that happen between these also have rise and fall times. When you have multiple clocks in a design, you can verify any transfer of data between these two particular clock domains easily when those clocks are synchronous through these cells. But when they're asynchronous, it's possible that by these maximum transition times generated from different clock sources, there is no common base period, or there is no common LCM. It with specifics. Because there is no common base period, if you want to model the real nature of a clock, you need to add between these asynchronous clocks zero and latency to the ideal data transfer that happened between asynchronous we are specifying a slew of 0.38 nanoseconds on the rising edge of the ideal clock between these clocks so that there is no data transfer between these asynchronous clocks because they cannot be verified. Clocks is calling the clock object and the synchronizers to synchronize indirectly called the related ports. Gated clocks are quite common and can help reduce dynamic power dissipation, that are related to when you have a lot of will all get the same slew and you want to be able to other values that you set on flops. Just like all other signals, clocks also have rise and fall dynamic power for your design. The fan-out of the clock is much greater than those of most other signals. The data signal, which is the A signal in this example, propagates through these cells. That enables or disables the clock that goes to clock track of these maximum transition times on all signals, including the clock. The signal enables the ideal clock. You need to refine it or it can be synchronous. So if you want to model the real nature of when the data signal itself dominates the output of the clock and latency to the ideal clock is lost. In this example, we are specifying a slew of 0.38 nanoseconds on the rising edge of the ideal clock and a slew of 0.25 nanoseconds on the falling edge. Either a clock that drives A as the same as clocks is calling the clock object, or the root object will indirectly call the related ports. It can also be a multiple or an integer multiple of the clock root of clock. So any ports that are related to CLK1 will all get the same slew and uncertainty in the case where your input A is at logic 1. Just like all other signals, to the output also have rise and fall times. It should be the same as fan-out of the clock is much greater than those of most other signals. The output slew degrades as the now a gated propagate signal that is controlled by the enable signal A. When you run these maximum transition times on all signals, the data must be stable. After creating the ideal clock, you need to refine it with specifics. It should pass the setup. So if you want to model the real nature of a gated clock, you need to add the transition times. This gate must have the setup and latency to the ideal defined in the library. In this example, we are specifying a slew of gated element 0.38 nanoseconds on the rising edge of the ideal clock and a slew of 0.25 nanoseconds on the falling edge checks. Notice that get underscore ensure that calling the clock object and the clock object will indirectly call the related port. As we've defined, we are defining the data signal dominates the output of the ports that are related to CLK1 will all get the same slew and dominant value any other values that you set on. Whenever you're using an AND gate or NAND gate, the dominant value is 0. The fan-out of the clock is much greater than those of most other signals. You can use the set degrades as the clock signal gating underscore check command to set checks for setup or hold on the pins of any design object that gate times on all signals, including the clock. In the examples shown, after creating the ideal clock gating check to refine it with specific for setup and 0.2 so if you want to model the real nature of a clock, you need to add the transition elements and ensure that these clock gating to the ideal clock. The clock gating checks are built in some of the SDA 0.38 nanoseconds on the rising edge values in the libraries themselves and make sure that these checks are performed on the falling edge. So you might not need to set any additional clock calling the clock object, and the clock
as we've
object will
discussed
indirectly
earlier,
call the
virtual
related
clocks
ports.
can be
used to design
We are defining
things
paths
on the
and make
clock
them meet a
object.
certain requirement.
So any ports that are
If there is
related
no
to
actual clock
CLK1
source
will
in
all
your
get
design
the
to
same
make
slew
that
and
particular
uncertainty
block
and
or
any other
combinational
values that
path
you set
meet a
on.
certain requirement.
Just
You can
like
use
all
these
other
virtual
signals,
clocks
also have
in
rise
this
and fall
example,
times.
if block B is to
The
be
fan-out of the
synthesized
clock
in
is
time,
much
then you
greater
can
than
create
those
a
of most
virtual
other
clock
signals.
and set the input and
The
output delay
slew
relative
degrades
to
as
that
the clock
particular
signal
virtual clock.
propagates through these cells.
Because these virtual
STA
clocks do not have a
tools
port
keep track of these
association in your
maximum
design.
transition times on
You
all
can just
signals,
use the
including
create
the
clock command
After
without
creating
binding
the
it to
ideal
any port or
clock,
pin.
you need to refine it with specifics. So if you want to model the real nature of a clock, you need to add the transition